You're listening to the Not Just Numbers podcast, a conversation with mathematicians on their work and their lives to get to know them and discuss common biases and misconceptions.
Hello everybody and welcome to another episode of It's Not Just Numbers. Today we will talk about so-called pure mathematics. My name is Marit van Straaten and with me is Marcello Seri.
Hi Marit.
Hello. And we also have two guests today, Jaap and Oliver Lorscheid. Jaap, would you maybe like to start introducing yourself? Tell a little bit in very layman words what kind of mathematics you're into?
Hello, thanks for having me here. Well, I'm Jaap. I've been in Groningen for quite some time, since '92, and I'm a professor of mathematics.
And what type of mathematics are you a professor of?
Well, it's called pure mathematics. I have a certain task, and the task is called geometry and number theory.
Okay, so how could you explain what that kind of mathematics is about to someone who knows absolutely nothing about mathematics?
So geometry is about figures. I mean, you have certain shapes, and you look at the shapes, and you try to either classify or understand the shapes or know why certain shapes are really in fascinating ways distinct. And number theory is about numbers, so integers, fractions. And the two things come together when there is a shape that is described in a way that also involves numbers, integers, rational numbers.
Yeah, that sounds very clear to me. Oliver, could you maybe tell a little bit about yourself and the type of mathematical work that you do?
So about myself, I'm also professor or associate professor here. It's called professor in Groningen at the Math Institute, a close colleague of Jaap. Actually, I'm working in the same group as Marcello, but I think topic-wise I'm closer to Jaap than to Marcello's work, which means I'm doing also working with geometry, some applications to number theory and combinatorics. So I can say a little bit more about this later. About my personal history is, after school I studied mathematics and did the usual path towards mathematics, and then I worked for several years in Brazil, and I came to Groningen only 3 years ago. So I did my PhD in the Netherlands, not completely new, but Groningen is relatively new to me. And about the math, so I think much what Jaap said is true for my work as well. And combinatorics is, imagine a Rubik's Cube and you're trying to solve it. So you're doing puzzles like this. So you translate a lot of questions of mathematics into these combinatorial questions and you try to solve it and you do something back about the original problems that you had.
Very interesting. Can I ask you something? Because if I open your website, at some point I read tropical geometry. And it's always a fun name. And it took me years to understand what tropical was about. Can you tell us something about that?
Yes, so the word tropical relates to Brazil, very coincidentally. There's maybe a small fun story connect to it. So first of all, the historical origin, this was Imre Simon, who was a Hungarian mathematician working in Brazil. He was not a mathematician, but a computer scientist, and he kind of invented the tropical numbers and worked with that. And later there were geometers picking up on this number system that he invented, and these were French mathematicians. And in honor or to mock Imre Simon, they called it tropical mathematics or tropical geometry, even though Imre Simon was not really working in the tropics. He was in Sao Paulo, which is outside of the tropical area. But then years later, when I started working in Brazil, I got into tropical geometry, which was more governed in Europe and in the USA, which was purely coincidental. And it was actually a fun fact that I was not the only one in Rio with this story, but we were, I think, 3 or 4 people doing tropical mathematics in Rio who just came together. So there was a concentration of tropical mathematics or tropical geometry in Rio, and we had the first conference there, tropical geometry in the tropics. So this was kind of fun. But I think you also asked about the content of tropical mathematics, what it's about, not about the origin of the name. And this relates very much to what I said and what was probably the hookup of you asking. This is one of many ways to translate problems from classical geometry, or let's say over the real numbers or complex numbers, into a more combinatorial gadget. So things will be finite combinations of certain things that you can understand much more easily than classical problems. I think I shouldn't go too much into depth here because then it becomes technical.
Thanks a lot. So it's quite fascinating that both things you said, including this aspect of looking at some mathematical field, say geometry, and some other mathematical field, combinatorics and number theory, and somehow using one to look at the other. So there is this kind of pollination between fields that somehow, as students, we might think are quite separate or distinct. And then I'm curious, did this play a role in you finding this topic interesting? Was something else? So how did you end up studying what you study? Jaap, would you like?
Well, I would call it sort of an accident. My plan was definitely not to start studying mathematics when I was in high school. I was pretty good at it, but I also found it exceedingly boring. So what I liked a lot was some of the languages. Like my highest grade was for German. And I liked German literature a lot. So authors like Lenz, I think I read everything that they have ever written.
So what make you change your mind?
So there were two things. One is access to a good teacher. So one of my high school teachers was also an editor of a high school journal for mathematics called Pythagoras. It still exists. And so I was fascinated by the way he spoke about the subject. I liked that, but still it was a boring subject. And then from my class, probably also because of the same teacher, 4 other students went to study mathematics. One became a lawyer in the end. 2 became high school teachers, and 1 quit. I didn't. But in the summer, I read a book by Douglas Hofstadter, a book called Gödel, Escher, Bach. And it was completely fascinating. It was a mind changer for me. I didn't know that this was also mathematics. You could, of course, argue that nowadays it's called fundamental AI or fundamental computer science, what he was doing. But it really was important for me. Not because of the philosophical aspects of the book, thinking about what can be proven and what not, but more the whole style. And so when I also went with some of my former friends from high school to classes, for example, in Utrecht by Professor van der Blij, back then he was a phenomenal teacher, I was very quickly hooked. So I changed from German to mathematics soon.
Wow, fascinating. How did you came into contact with the book? You just found it randomly or was recommended?
I guess there must have been an interest in science. I don't know how I got it.
This is fascinating. I love these stories, right? It really shows and relates with what we were saying in the first episode, that sometimes you don't know and you find out very late, but this doesn't mean that it's not for you.
No, definitely.
Oliver, was it similar for you or different?
There are many similar aspects in my personal story. So I never intended to study mathematics principally. So as a kid, I was mainly fascinated by physics. So by the very big things and very small things, which means astronomy and particle physics. And I think in my early childhood, Einstein was a big hero for me. And then later I read this book by Hawkins, which I think was another step towards being very interested in physics. And in mathematics, I had a similar experience as Jaap. I was good at it, but was boring for me. And the thing really shifted when I entered university. So I wanted to study physics, and then you take math class. In the first year where I studied, you take all math classes you use for mathematics. And then I learned in a couple of months that I really don't want to study physics but math, because I felt that lectures at university, they reveal a very different appeal of the subject. It's totally different what's taught at high school. And I was very much drawn to the elegance of mathematics, and I could understand it easily, while physics was a closed book with 7 seals to me. I simply didn't follow the lectures.
I see. Very, very interesting.
It's also quite funny to see that you both had the experience of high school mathematics versus university mathematics and the appeal in the different type of courses. Did you both always know that you wanted to pursue a career in mathematics, or has that maybe just been thrown into your path? Jaap?
No, first, once I entered mathematics, my feeling was I would become a teacher, because that was the only thing I knew that mathematicians could possibly do. And it takes a while before you find out that there are professional people in life who have studied mathematics and found a career either first outside mathematics, and then even later you find that it's also possible to pursue a career within mathematics. To get there, first of all, you have to make up your mind whether you're good enough for that. Your feeling is that there are all these colleagues who are much more suitable for it, and really brilliant people. It's like juggling. You have people who are very, very good at it, or sports, and then you do it on a sort of low level. And the other aspect is luck. At the right moment, there should be a job on the right level available for you. But by the time I was at the end of my PhD, I was really looking into jobs within academia.
What about you, Oliver?
I think you should have chosen 2 people with more contrasting experiences. For me, it was, as I said, in the beginning when I started studying mathematics, I was not thinking about studying mathematics, but I decided soon for mathematics after 1 semester. This was clear for me. But at the same perspective, I said, well, I see where it will end up. So I didn't find my limits until then. High school mathematics was easy, as I said. And I didn't know if I was made for research or not. So I always kept this open, and I had the same plan as Jaap. So if I can become a high school teacher, I like teaching. I liked it at that point. So I was very much imagining myself with a career for high school mathematics. And this stayed my plan B for quite a while. So even during the first postdocs, I said, okay, if this doesn't work out, I will become a high school teacher and I will be happy with that. And this, I think, was a very important psychological trick for me to get easily through this postdoc phase, which is very stressful for other people who really aim at this career in academics and who then have to apply for the next job and the next job and the next job. But yeah, in my case, there was a very large portion of luck, I would say, that I made it through this postdoc phase and stayed alive in academics.
I particularly like that we also talked about luck, because I completely agree that, and it also reflects with my history, that you need to be good at what you do, and you underestimate usually how good you are at what you do, but you also need the right job at the right time, multiple times, to make sure that this can happen and go through. So we can't ignore the fact that we might be very, very good, but if we are not lucky at the right moments, that might not be enough. I'm also curious about something else, right? We have heard what you do, we have heard how you got there, but what is your drive? What is your main motivation? What is the thing that lights the sparkle when you work on your topic? We usually start with Jaap, so I'm asking Oliver now to start.
I have to say that there are different aspects of my job, so let me take this out of the way. There's research, there's teaching, and there's administration. And I think my heart goes with research and teaching, which has different appeal to me. So for research, it's really this drive of solving a problem, of gaining more insight, creating more understanding for something. And I mean, it has many aspects, but this is something very appealing to, right, shaping a problem, to framing it, and to working through it until the point that there's maybe a research paper at some point, or I can present these solutions to others in a research talk, which are the benefits after many months or sometimes even years of research. And that's a very rewarding activity for me, so that I do it basically in my free time. Nobody counts hours for that, so it's really me who determines that. And I also like teaching, as I said before, and this is rewarding on a much shorter notice. So you give classes to students, and you typically, if you give a course, you give it 2 lectures per week. So you prepare for it and you give it. And then the rewarding experience is really that I establish communication with students. And, well, to be honest, that I have to phrase it like this, that I get the perception of students understanding some material. And I guess feeling this connection to students and getting this feeling that students really learned something from my activities, that's the other rewarding aspect of my work.
Is there? Let me ask something here, because I'm very curious. So this solving a problem and finding new ideas and perhaps helping others solving their problems with your new ideas, this kind could apply to all mathematics. Does it mean that going back, if you had, for reasons, taken a different direction, you would have been happy doing other mathematics because effectively the part of problem solving is the one that drives you? Or there is something specific of the things you work on that excites you?
Yes and yes. So I'm totally sure that I would be happy doing something different as well, if it has this, I would say creative aspect, that I can determine myself a little bit where it goes, that I can solve things, that I can bring things to a conclusion my own way. And this is not so much bound to the mathematics that I do. But I also experience that I'm good at certain parts of mathematics. So just to give one example, which will not talk to people who don't know that in more detail, but I did my PhD on automorphic forms, which is part of analytic number theory. So there's a good portion of analysis inside, which I understand up to a certain level, but it's not my strength to work in analysis. So I probably would have not succeeded the way that I did like here, which means to wind up in academics or something like that, if I would be forced down a path in analysis. So I really have a fable for algebra, geometry, combinatorics, what we talked about before.
Thanks. Sorry for interjecting there, Jaap.
Yeah, your question reminded me a little bit. There is a famous discussion some 15, 20 years ago where people subdivided mathematicians in 2 types. You have the types, let's say the theory builders, the people who look from a distance and look at an overview of theory and are able to build. And you have the laborers, the ones who are on the floor and work very hard on a tiny aspect of this huge landscape that others build. I think in order to appreciate mathematics, you do need to be something of both. Because if you only see the tiny bit around you and try to solve your way through that, the appreciation for it is somehow lacking. I mean, you can be rewarded for being able to be the one that solved some little problem or was able to find a solution to some thing that others found very difficult. But what it's good for and what the broader aim of it was remains hidden even for you. And I think what is said here is particularly true for we call pure mathematics. In pure mathematics, you very strongly have, but it's like a culture, and you're building on part of your culture. So you can maybe in some sense compare it to the culture that you have in art, in music or in painting. I mean, there's a certain way that is particularly appreciated in a certain period of time. And then you look at it at a later time and have new techniques or have other ways of appreciating things. And then you can use the new ways of building upon the older ones. And this type of art is typically very much appreciated by people in pure mathematics. And to build upon that gives a reward in itself. I mean, you have the big names of former centuries or even present days, and you look at it, and then all of a sudden one of us is able to add a little contribution to that, or to have an interpretation of it that is distinct from the way it was originally done. And that is very, very rewarding and also helping, because this new way of looking at it helps others to go even beyond what you did. So this is sort of I would say the cherries on the pie of our type of mathematics.
I think that's a very interesting view. I was wondering, were there any big challenges that you guys faced up until now in your career, Oliver?
Yeah, I think that I confront challenges on many different levels. So I should maybe pick some major challenges on the way. I think I was never challenged in my decision to do mathematics. I always liked it. I also had a lot of other interests at the time that I still had time for this, which was pretty much before I had a family. Once I had a family, I had to concentrate more on my family and the job, so there was little free time. But the joy or the contemplation that my work gave to me never made me doubt what I do. And I mean, there's maybe a philosophical challenge about the value of my work, but I think I'm also satisfied with the answers that I can give in this direction. So in this way, I was not challenged, but there were maybe some major, I don't want to call it breaks, but some major turning points in my life. So the first one is what I mentioned. Our first child arrived in our life, and then soon after the second child. And this meant that the way how I was dealing with everything was totally different, because a kid, especially in the first years, needs 24 hours of supervision. So the priorities were totally shifted. I had to do totally different time management, and this was hard in the beginning, but at some point you also get used to it, and you don't do mathematics for stretches of hour in a time, but you do 5 minutes here, 5 minutes there, and you just have a different method of working. And then another major challenge was when we came back to Europe as a family. So my wife, Cecilia Salgado, also works in the math department, so we faced the problem of finding 2 positions. And even though it was kind of a long-term plan to at some point go back to Europe, this was getting very urgent at some point when Bolsonaro got in power in Brazil, which was a government that we really didn't like to be part of in any way. So all of a sudden we wanted to find a job here, and this was a very hard year for applying for positions and so on. And we were very, very lucky. I think this was the most lucky decision in all these decisions were responsible for my way, that we found 2 positions here in Groningen, and we're very thankful for that and really appreciate that.
Yeah, thank you. I think they're very insightful challenges. Jaap, do you have any challenges that are similar or maybe not so similar to Oliver's?
And as Oliver said, the word challenge can mean many, many things. inside mathematics, you have challenges of very different types. I don't know exactly how many years ago, but at some point in the Netherlands, we obtained the possibility of making a system that would increase the number of high school teachers nationally by offering math courses to people with a different background than mathematics. So you're a chemist and you would like to become a high school teacher. So it began with making a kind of table. People with this background need to do these courses. And so this was a table agreed upon on a national level. And then because of the table, a certain number of courses had to be set up. The government even had money for that. And I found it a huge challenge to set up one of these courses, because it really has an effect on what type of background a high school teacher has. It's a new type of student. It's not one, it's not only the chemist, but it can also be someone who has worked for companies for 20 years and has an engineering background. So people are very different. And this is an example that also was very rewarding, because at the end, this whole program has brought hundreds of new math teachers into the Netherlands system of high schools, which is good. And it's also one of the ways in which universities are very much involved. But the word challenge is so broad, you can bring it almost anywhere.
Definitely, yeah. I can imagine that having to design a course for people who do not have a particular mathematical background can be quite hard once you're into mathematics yourself. Yeah, thank you for your answers.
I am also another curiosity now, which also can relate to this. So you both said that you found mathematics boring in high school. And then I'm wondering, as somebody that experienced it in that way, what suggestion would you give to somebody that is not yet sure if they like mathematics or if they want to pursue a career in mathematics, if they would like it or not, since we kind of all agree that high school mathematics is different from university mathematics. And in parallel, do you think is there something we can do to connect with high school and show to high school that mathematics is much more than what they see there?
First of all, I think every mathematician has a task here. Namely, the task is called outreach. And there are various platforms in which we can use that. So we can try to some of the appeal that we ourselves have within mathematics, or some of the topics that we know that may not even be so close to our own research of the day, but are very attractive and explain some nice aspect of mathematics. We can bring that to high school students, to their teachers, and platforms for that exist. Here in Groningen, we have the College Carousel. On the national level, there are various things organized for high school teachers. So whenever one of us is asked, or even if we are not asked, we can just offer ourselves as potential speakers for that. We can write texts for that. And the text is not a new thing in the research that we do, but is something that shows our pride of our topic. And I think we should all be aware of such possibilities and invest some time in it.
Yeah, and there is Pythagoras that you mentioned was very influential for you. We can add the link in the episode notes later. Oliver, what do you think?
I think I have a very similar view on what Jaap explains just now. I think that more mathematics on, I don't find the right words, on an academic level should brought to high schools in packages that can be understood by high school students. And I think this can be done by us, so everybody who's at the university, to go to high schools and talk to students in terms of some little workshops or something. This can be done in form of print material. I think Pythagoras is an excellent option to reach high school students. And I think there's one point which where things even got worse compared to the education that Jaap and I had, which is that math teachers are not taught at university anymore, but they have their own institutes where they're educated. So somehow the direct teachers of high school students are getting even further away from academic mathematics, and they maybe lose this inspiration that they could get if they were kind of embedded in a university where they learn mathematics.
I mean, this resonates a lot with what I think about it. I think we have somehow, it should be part of our job to reach out and not just stay into the university close to our student, but somehow try to bring across the interest, the passion, the multifacetedness of our of what we do and why we like it, why we think it's important, and why it has been important in the past and why it will be important in the future. But I think I'm not sure this would be enough. I tell you what I mean. There is very often when you talk with people, I don't think this is just my experience. You hear that either they like mathematics in school, but more often than not, they find it so hard that this was something that only geniuses can do. Nobody else can do it. Just few people should do that. And somehow this construct walls, right? As a student, I keep hearing from my family, from people around me, math is something hard, math is just for a few people, then I don't know, I would be discouraged a priori to do that. And perhaps it's not enough that we look out for high schools, and perhaps it's not enough that we look out for teachers. Perhaps we should look in general more at reaching a wider audience of different ages, so that the culture around the kids is also a culture that says that, look, if you like maths is for everybody. It gives you very interesting tools also for other jobs. If you don't like an academic career, it gives you tools to become a teacher, but it gives you tools to become a programmer, to become data analyst, to work in finances, to work in so many different... I know people that do image analysis from satellites, which effectively is spectral theory. So it's actually a very powerful toolkit for many other jobs. And it's not about being a genius, it's about putting in the effort, as you were saying earlier. And if we restrict our view to just high school and teacher, perhaps we're missing out that a lot or some part of the society around, especially in certain areas, would be still fighting against mathematics or certain types of science, in the sense that they are very hard and you must be from a certain type of background or with a certain mindset to do that.
You are right, but at the same time, an appreciation for scientific thinking doesn't come from how you learn math, or it comes from somewhere else. It's almost a historical realization of the world we live in, and appreciating how we get to a certain point. I mean, you can teach solving quadratic equations somewhere at the beginning of high school as a tool for solving quadratic equations. But in a way, it's the most stupid tool possible, because in the end, you know that a solution is some rational number plus another rational number multiplied by a square root. And of that number, you can't even compute the first two digits. Or you can, but it takes an effort. So in a way, a numerical way, that gives you, okay, the solution is approximately 0.57 something, is much more helpful for society. So in order to appreciate the other thing, you have to tell something of the background of such a formula. Where does it come from? And what can you do with it, apart from using it to lay your hands on the actual solution? And that type of more background material, take a step back and look at what we have. That's not taught at all in high school. And I also wonder, there is no time for it, and maybe a part of the high school kids wouldn't even be interested.
I mean, I agree and disagree in the sense that probably a part of the kids, there is always somebody that is not going to be interested. I mean, to each their own, right? There will be people that like and there will be people that don't like mathematics as for any other thing. I agree that it gets much more rewarding if you see what's around, but it's also get much more rewarding probably if you start playing with it, like playing in the sense, okay, I have this equation, but then you can see that this equation sometimes has 0 solution, sometimes has 1, sometimes has 2. So it's not true that there is always a solution. So how do we know when there is a solution? And then you can see there is a pictorial way of thinking about it. And this pictorial way, once you understand it, gives kind of a direct way of thinking about the brute formula that you're writing down. And both have different beauties. And even there, if you think at high school, if I think at high school, we have one of the hardest concepts probably there is thinking about infinity, thinking about limits. And you can play with that, right? We were doing some times ago this promo mathematics thing where we were introducing students, and it's very easy to make a 20-minute talk where you're just showing that you can make figures that are finite. I can draw them on the board, but are infinite length, or that are infinite boundary, but at 0 area. Like playing with weird things. Mathematics is full of such weird things that challenge your intuition, and that somehow makes it, at least to me, and probably at the epsilon of people, the things like me, it challenge the intuition and show that there is so much more you can do and it can become playful. And I guess Pythagoras does something similar. It shows you very fun, weird little problems that somehow challenge the way you think about mathematics. I remember in high school, our second year of high school, our teacher started giving us problems with, there is this city that is built of bamboo stick. Everything is measured in bamboo stick lengths. And we had to find where to put a certain door so that across the door on the other side of the square wall, we would see a certain tower. And we should give the answer in bamboo stick length. And even just trying to figure out how to remove this bamboo stick and not worry about this bamboo stick was kind of a challenge. And some people hated him, some people loved him because of that. It was super weird and it made it interesting. The same way, once he gave us a problem that is impossible to solve. And he wanted us to say, okay, we tried everything we know, we can't solve it. Of course, none of us did it. We all got a 2 in that exam. But it was actually, and then in the end, he scrapped it. But the whole point of it was to show us that it's quite common that there is no solution. And I remember up to that point, I had never, ever even considered the idea that if I get a problem, there might be no solution to the problem. So I think it can become a tool to challenge intuition and not a tool to just learn formulas. But I think if we present this to both students and their parents and the people around them, we have more chances to make a difference than just going to students that are still in an environment that says, but this is rubbish, you should just work on something useful.
Yeah, you're right. So it means we have to reconsider the balance between, you still need to learn certain skills without thinking too much, and just do the skill, because the skill is so useful in solving certain problems in biology, in physics, in chemistry, in any science at all, economy, not to forget. And that's mathematical skills that you need to have. And unfortunately, the majority of high school consists of simply learning those skills without learning too much of their background. And it's exactly the background that opens a way to the mathematical, scientific approach to making it research in the end. Yep. And giving it a little bit more of that flavor would probably attract a certain type of student and parent and teacher. But it means we have to expose them to that.
Yeah, I agree. I mean, I think that's part of our duty to try and rethink how we do things in a way that is more constructive and more inclusive, more active. I mean, these skills can come with practice. You don't have to memorize them. If you make something that is so fun and so interesting and so different that people engage with it, then you will get some of the people just because they just play with it.
I also sometimes feel in high school that a lot of people view math as you have to learn these rules. And I had a teacher in high school who indeed, as Jaap said, showed the intuition behind the unit circle, behind the logarithms. And then you don't have to remember these rules anymore because you know what is behind it, how it works, and then you can just remember that on the test and you don't have to remember all these rules and that get confused by them. So I agree with Jaap that that's a very important step to take, to show people that there's more intuition behind math instead of just having to learn how to compute the roots of a quadratic formula.
Yeah, I mean, I fully agree. I actually admire teachers. They have such a hard job. You have to involve young students that have a billion interests and a billion more interesting and pressing thing to do, and find a way to get their attention and bring them along with you. It's, yeah, I have high admiration for them. So I've derailed the conversation a bit, but I was really interested in discussing this point. Thank you very much. Before we move on to, well, you mentioned at the beginning you work in pure math, and at some point we want to talk about that. So before we move on, we had usually one more question. This is about showing that mathematicians are people like everybody else. And I think at this point we have passed this message, I hope. But I'm also curious, what do you do outside mathematics in your free time? Oliver?
Now at times I find free time again a little bit. So for a long time I did do basically nothing outside of math. But nowadays it changes over the years. So I cannot say I have a constant hobby or something. So one thing maybe to mention is during the pandemic where I stayed a lot at home, I surprisingly had a lot of free time. So I could spend several hours per day to do Tai Chi and meditation, which I lost a little bit with moving to the Netherlands because things got more hectic again. And then I also lost the routine and the stamina to do that, but also like to listen to music. I think jazz is my favorite genre, but also other music. In principle, I like to read a lot. I like it a lot, but I cannot do it a lot. So normally I just pick a book during vacation. But I remember from my high school times, I was also reading mainly German literature as Jaap, which is maybe more natural for me since I grew up in Germany. Yeah, maybe.
Already sounds like quite an impressive list, right? Yeah. What about you, Jaap?
Well, let's begin with sports. Every Tuesday evening, I play volleyball.
Oh, nice.
For many years already. So and that's my sports activity, apart from riding a bicycle to university, if possible. And music. As a child, I learned to play organ, very old-fashioned instrument. And living in a village with a church very nearby, some evenings you can find me with the key of the church, going there and without too many people listening, preferably nobody. I do that. In the local church in my village, I'm also active in the board of the church, that type of thing.
Yeah. Oh, organ. You don't hear that very often. That's really cool. Yeah. Do you still play it sometimes in your church?
Yes, yes. Yesterday evening.
Oh,
example.
impressive. Nice.
Beautiful. Thank you very much. Okay, so I guess let's take the elephant in the room and start analyzing it for a while. Pure mathematics. So first of all, how would you define it then?
Now, for me, pure mathematics means it's more like an attitude towards mathematics. For me, it means the reason why you pursue a certain problem is not so much because either physics or something in econometrics or in industry needs a solution to it, but it's really the curiosity, the challenge of having a solution for that drives the research. And of course, you can call that a little bit pedantic, because we are all researchers who are paid by tax money, and then we do these things that drive our curiosity rather than what is good for society. Yeah, you could say start from there. The fact is that in many centuries of mathematics, that was the way it went. It may have started very long time ago with wanting to know how high a pyramid needs to be, or how you can measure certain sizes, and you name it, to predict when the next solar eclipse happens, and so that type of thing. So it started with really applied problems, but very much of the mathematics, even of 2 millennia ago, come from these curiosity-driven things. And that's still the case. You can see that not only within mathematics, that many of the major prizes and rewards that are given to mathematicians for their contribution to the field, I mean, sort of the Nobel Prizes like equivalents in mathematics, are usually given to things in pure mathematics. It didn't change when the times became a bit more modern. In Germany, there is still the Journal für die reine und angewandte Mathematik, both the pure and the applied mathematics, a journal of more than 200 years old. And it's in fact a pure journal. What we define as applied mathematics, you will hardly find within the journal. Yeah, so did I give a definition? I don't know. I gave an attitude towards it.
Well, I think that's working as a definition. Oliver, do you want to add something?
Yeah, I think the term pure mathematics has different shades to it and is used very differently. So what Jaap explained, I think, touches one side of it and gives a very good explanation. But to just name a few other aspects. So normally when I say pure mathematics, I use it in different meaning. I mean it as a collection of sub-areas, which are normally attributed as pure mathematics opposed to applied mathematics. And many departments of mathematics are divided into a department of pure mathematics and applied, or you have programs of studies which are in pure mathematics and applied mathematics, which is the case in Groningen. So it's, for a good part, a practical subdivision. There's also maybe a simple philosophical definition, which is correct for a large part of the way, but then becomes problematic if you look under the hood, which means that pure mathematics is mathematics that's concerned with problems within mathematics itself, opposed to mathematics that tries to solve problems outside of mathematics and physics, I don't know, computer science and other areas. Here in Groningen we have a big collaboration with the Seri, with medicine, all these kinds of stuff. So what I want to say, there are different ways of using it, but there's something which I feel was maybe implied by your question, Marcello, and which is maybe a nice thing to discuss. This word pure is, I think, not a very fortunate attribute to mathematics, because it implies something on mathematics that's not pure by forming the opposite. I think it's, even though this is maybe a minor detail, and normally I don't think about that when I use the word pure mathematics or applied mathematics. But if I look back at it, it's coupled with certain attitudes that you have. So as a student, I was drawn to pure mathematics right from the start for several reasons, what Jaap mentioned. So it's really kind of this curiosity that I want to have. But it's often also that, I perceived as students that it was labeled as the harder type of mathematics. That's really the hardcore where you go into, and somehow as a young person, I was appealed to that. I want to experience what's really the hardest thing that I can do. Not that I felt that I was so particularly good at it. As I explained before, I didn't meet my limits at that point, but was more really to see how far can I go, what can I do, and so on. And nowadays, I don't think it's like that. I think that other types of science are as hard. I mean, there's no harder or so on. It has different kinds of aspects, different things that you can do. I mean, pure mathematics is one of the science that has the largest pile of theories that you need to learn until you can do something. So this is maybe a fact that you can defend, and that I believe is true. There are other areas that are very theoretical, but there are other types of mathematics which often come to applied mathematics where you're touching research much earlier because you don't need to learn so much background theory. So in this sense, it's maybe harder. But you also lose certain aspects of research if you just look at the things that you need to learn, because research is not just learning a lot of theory and then applying it to some problem. But to do research, you need a certain type of creativity, and this you need as much in pure mathematics as in applied mathematics, as in physics and other sciences. So you need to get a certain, so you need to define your problems. What do you work on? Which is non-trivial. You need to define the limits of to really know what you're working on. Otherwise, you're playing around and you never get somewhere. And then you need some ingenious idea normally to do something. Well, there may be more mechanical ways of dealing with the project, but normally, and this maybe links to the attitudes that Jaap mentioned, it's there's some idea, some creativity that goes into research, and I believe this is as much true for pure mathematics as for other areas. So in this sense, I think this word of pure is kind of passing along a certain attitude that I find is maybe not too fortunate for many people, including myself as a younger person, I would say.
Yeah, you mentioned that you perceived the pure mathematics as the harder type of mathematics. Where did that perception come from? From your lecturers, from your fellow students, or how was it installed in your brain? Because I'm just curious to know.
With me, was my fellow students. So I was a first-year student, and then I had older students somehow who were saying, I should go for algebra. This is the hardest courses. I mean, they didn't say that you should go for it, but they were saying these are the hardest courses and so on. And then I thought, okay, let's challenge myself. Let's aim at it. And I mean, just to be clear, I didn't go for it in the long run because it was hardest and I just liked to suffer or something or to prove myself. But I felt that I have a liking for it. It's really the type of thinking that resonates with me, and with other courses I felt this less so. But the initial step, I think, was really that I was searching for the hardest challenge. And I don't know if someone would have told me that some other area, I don't know, functional analysis, the hardest area, then I might have ended up there and went for that first.
Oh, that's interesting to hear.
I like this answer in the sense that it resonates with my experience. And first of all, yeah, indeed, we're using a term that perhaps doesn't do any justice to what it means. But the way it resonates, if I think about my career as a student, I started thinking of becoming a mathematician when I found that I liked a lot analysis, real analysis. Not calculus, but the abstract part of theorem proofs. And I really liked the way Cauchy, Rolle, and Lagrange theorem were intertwined, actually. That was one of the things that clicked for me for some reason. And when I was there, I was drawn. I started loving logic and algebra a lot, really a lot. And I moved toward this more and more abstract thing. Somehow that was the hardcore thing. And somehow I could do it. And also I was starting to discover some elegance in it that was very attractive. And then when I was there, I found out that you could use analysis and geometry to study algebra. And And then I went back to analysis, basically. And then they started mixing. Then I found out that what I was liking was actually how they mixed up together. But it was always in a very curiosity-driven part of mathematics and very much not connected to reality, until I found then that there is quite some benefit for me to know that the mathematics I'm doing for the sake of it and to understand, actually had connection with reality. Even though it's probably useless in physics in the sense that physics has moved on in their experiments and in the numerical simulation, still knowing the connection with the real world was helping me making a mental picture of how things could move, how things could change, what was the structure of the thing. And at that stage, I somehow questioned, is this now applied? Is this now pure? Is there any reason to actually distinguish pure and applied math? So I told you at the beginning I have an agenda, and the agenda was coming to this point, in fact. Because from what we say, I agree with the way you started, Jaap, that perhaps there is a philosophical attitude that is different to the way you are thinking about your problem. Because the aim that you have is different. Even when it's both pure or applied, curiosity-driven, you have more or less connection with the applicability or problem that are from the real world, or developing the theory without knowing if and when a problem in the real world might arise that works with that. But all in all, it's all mathematics. You can be a bird or a frog in pure or applied, as in physics, as in biology. And sometimes you can move. I remember when recently we started these works recently, it's now 5 years ago. God, time flies. On numerical integrators. For me, this is pure in the sense that was done because we needed to understand something in our theoretical problems. It's extremely theoretical as a work. I mean, it's actually differential geometry and geometric mechanics. Yet it's usable in practice as a just fact of life or as a chance. And then I was talking to people, some friends, and they say, "Oh, I've seen you moved to very applied mathematics now. You're doing application." I say, "Oh, I don't know. I'm always the same person. I'm always doing the same kind of mathematics in my mind." But we have these silos in our, I don't know, probably because we are used to it, that keep this distinction alive of having a type of mathematics that is for the sake of itself and a type of mathematics that is for the sake of problems. And with this long discussion, sorry, I've been talking for 5 minutes. What I want to go back to the societal relevance, because you mentioned that we have this attraction, this thing that doing the mathematics perhaps is not societally relevant. But is it true? I mean, I think we have to revise what we think about being societal relevant, because if we think that something is societally relevant only if it can be applied in a matter of 2 years, I think we will be destroying science on the long run. I mean, part of doing fundamental research, applied mathematics, whatever, I think is also having the space and the time to challenge your hypothesis, challenge your intuition, and push for the frontier of things that you don't know how they're going to go. And as such, they might take, you said also before in your comment, years to get an answer, decades perhaps. And you might not even know that there is an application now. You're doing it because you think it's important to understand why a certain hypothesis is there and what happens if you remove it. It might enlarge a field, it might connect to different fields, it might allow you to bring a theory from one place to the other. Whatever happens is for the sake of knowledge. But this is a knowledge that maybe one day will bring an application, maybe not, but is developing knowledge. And we will never know if there is some additional societal... I think this is already societal value, that we are bringing forward knowledge and we are constructing a better understanding of this language that is then also used to describe nature. And then perhaps in years' time, there will be an application. But if we start with application in mind, then we are basically precluding a lot of possibility, because it might be that we need to go very, very far away around our problem before we realize that there are some analogies that can lead to an application.
Yeah, that's exactly it. You cannot predict where the application will be. There are many examples where the theory came first, and well, a famous example is, or at least was mentioned in Eindhoven 20, 30 years ago. I mean, in Philips, they were developing things that in the end led to compact discs, and they sort of had an engineering way of making them, except they were not sure they could ever work because cars bump and whatnot. So there had to be some error correcting in it. So they asked the people at the university, and they said, "Oh, but we have that theory. We have had it for many years. Here it is." And 1 year later, the first prototypes were there. So that happens a lot, that mathematics is ahead of the actual application and the actual use. But even apart from that, like in the UK, was it last year or 2 years ago, there was this huge bond report that was made to convince the government that more money should go into the exact sciences, and particularly into mathematics. And there they made a case for showing the percentage of society that actually uses mathematics, and not just mathematics of centuries ago, but present day research results in mathematics. And I don't have the numbers straight here. But it was sort of an amazing percentage of society that had an immediate mathematical use. So, yeah, it is definitely there. The question for us is more, okay, it may not be our drive to do what we do, but we should certainly make sure that for societal relevance, we write down things and we communicate things in such a way that when society asks for them, we are ready to produce. We have it for them.
I really like this answer, especially the last point you make. That I was worried that at some point you say when we apply, we should show how this is used in life, but no, that's not the point. And I really agree with that. It has to be in a form that can be disseminated and then can be offered at the moment somebody needs it. But having the application there should not be the prime purpose of that, because otherwise it would defeat the purpose a priori, I think.
Yes.
Oliver, you said when you were talking that you are satisfied with the answer you give when people ask you why you do what you do and what it's useful for. So I'm curious on what those answers are and how it relates with the discussion we are having.
I agree very much with what Jaap said. Maybe there's a little bit that I can add, which is that mathematics is divided into, I don't know how to call this, sub-areas. So you have the big fields of mathematics, which is analysis, algebra, geometry, and so on. But in there, it branches very finely into sub-areas where people research around certain problems and certain questions. And this is normally a mixture of all of these areas, as we discussed with our personal experience, that we know a little bit of algebra analysis and everything that was mentioned before. And these sub-areas, they're normally guided by certain questions that arise somewhere. And these questions are normally very meaningful. So we're not creating random mathematics when we do research, but they're guided towards something. Even though if you take a single paper in some area, then it's very doubtful to see how this ever will be relevant for practical purpose in the future. So you could say, well, if we discard this paper, does this change anything? Probably not. I mean, could argue about the butterfly effect in mathematical research. But these guiding questions and the main goal that we're working to in the sub-areas, these are meaningful, and many people think a lot about what's happening there, and you're just steering to a goal if there's enough resonance between researchers. So it's not run one researcher who thinks he needs to solve a certain problem and he goes in this direction, and he might be totally wrong, but it's a whole community of 20, sometimes 100 researchers worldwide who are going in this direction and who have a common perception that this is important for future development, maybe within mathematics, but maybe within science itself. So even in pure mathematics, you're thinking about that a lot. And money within research agencies, it's also steered towards these problems that seem to be meaningful for future. So as a community overall worldwide of mathematicians, there's really a very good sense of what's meaningful for future development, what's not. It's not just randomly done. So just want to add this aspect that as a community overall, we have a very good sense of what might be applicable in future and what, I don't know, society or science overall might need in future. And the other aspect that I want to raise is that doing research is very important for teaching, in the sense that a class, the same class, let's say in analysis, given by someone who just did a complete math studies and is totally capable of transmitting all the facts, is given completely different by someone who's active in research and has a broader horizon of research problems, of proof strategies, of presenting mathematics. So we need active researchers to give these classes to people who study at academics to bring over the spark. It's the same what we discussed about high school mathematics. So this was boring for Jaap and me, or let's stick to my example for me, because I had teachers who never brought up problems like bamboo sticks that you mentioned. So if I had this before, then it would have been very likely that I thought, oh, math is so cool, I want to do that. I need to go to university to see people who can transfer this aspect of mathematics. And then I was fired for it once I had was particular teacher in linear algebra who would brought up topics that were much beyond linear algebra, but frame it inside this topic. And so if I would have been taught linear algebra by someone who was not a researcher, I doubt very much that I would have ended up as a mathematician, but I would have found it boring as high school mathematics.
I think you're making a very good point. Can I ask something about something that you mentioned? Because if you're not in mathematics in the field, it might be, kind of a question. If you don't look at the outside world as an inspiration for your research, how do you find inspiration for your research? How do you base off, okay, this is something that I can solve, or this is something that could be particularly interesting? How is that, how do you find such research questions?
Yeah, this is very much guided by what I tried to picture before, that certain communities, sub-areas have certain aims in mind where they go to. So I'm orienting myself on these aims, on the resonance within the worldwide community in mathematics, to find problems that are interesting, that and I want to interact with other mathematicians. This might be in a direct collaboration on a project, but also to produce mathematics that's useful for others, that others use to continue doing research. So this is a little bit my compass to find interesting research topics. But of course, I do this within the framework where I'm capable to do research. So I had this as a younger person. I still had this idea that, okay, let's go back as a very young person, as a kid. I was inspired by Einstein, and I thought, okay, it would be great if I could contribute something to a big theory. Nowadays, it's called a big unifying theory of the universe. So, but in a very naive way, I thought as a kid, I want to contribute to that in some way. And then I think during my studies, at some point, these ideas came back, and I thought, okay, it would be great to do that. But I was too far away from that. And nowadays, I would say it's impossible. I would need years of preparations to do anything in this area. So I'm just refraining from it. And I look at what's capable, what's within my reach, and what's interesting to work on. And then it's also a little bit the question, before I start working on something, I need some inspiration, some idea, some angle to get to a problem. Without that, I think personally there's maybe no attraction, but I also think the chance for success are very low. I mean, if I just say I want to solve this problem and I sit down for several days, then the outcome might be zero. So I always start with an inspiration, which might come very randomly. I see a problem in a talk and I think, this connects to something else, and let's find out more about that. And then it develops from there, or it doesn't in many cases.
Okay, yeah, it's interesting to hear that your inspiration comes from different sides.
In my experience, there is also the fact that sometimes you have some big question in your community, and then many people are steering attention there, and then very soon there are 2 or 3 answers coming, and sometimes you think, okay, now it's over. But usually the answer that come open way more questions, because some of them could be tweaked so that you can remove some very important assumption. Some of them are saying that something is completely impossible, and then you would like to know, is it possible anywhere? So they're usually kind of not the end, but the beginning of way more questions. And it's not even that long of a timeline. So I've seen this in my field at least 3 times in 15 years. So it's probably quite common.
Yeah, and so it means you need to have your eyes open.
Yeah.
And that happens in various ways. That happens by being present in this very international community. So it is really important to go to conferences. It's also important to sort of stay aware of what is happening in your field. So to read preprints, or at least read the introductions to them. And there is a big aspect of also luck here.
Mm-hmm.
I mean, everybody from his or her own background looks at a certain problem that's out there, or a certain solution that's out there, tries to understand it with the background that you happen to have, or come up with a special case that might be easier to solve than the general thing that comes from your background. And then all of a sudden it turns out, well, or it looks possible. And this decision, shall I pursue this? Or it's still, okay, I have a special case, but it's still way too hard, so let's not waste time on that. I think you get a certain experience with that. At a certain point, it happens less often that you run into a track that turns out to be a futile thing. And you can also, I think we very fortunately have very many bright students around. So you can experiment with that. It's not that you experiment on the students, but you try a very small case of something as a bachelor's project, as a master's project, and more often than not, more comes out of this than you would have expected at first sight.
Yeah. Although I'm still in the phase in which I have more things that remain pending, half done or stuck, than things that I know, okay, that's the answer, done, move on.
Yeah, true. And probably that will remain the case. I'm sorry to
No, it's
this.
fine. I mean, I don't mind that. I enjoy it. I have a curiosity now, so I would like to ask Marit, your point of view as a student. What do you think about what we have talked so far?
I agree that the name pure mathematics, as Oliver says, sometimes insinuates something. And as a student, what he said about algebra being the hardest has also been conveyed to me. And I've also been trying to think, how did that message come into my mind? But I don't know, I can't remember. Maybe it's because algebra, you have a lot of different courses from it in your bachelor. And I think that also the distinction between applied mathematics and mathematics as a student is also very much based on the difference between the bachelors. So you choose a bachelor either in mathematics or in applied mathematics. And only once you further in your academic career. So for instance, now I sometimes talk to people who do applied mathematics. And I find that there's not that much difference. Sometimes there is, but a lot of it is kind of related. It's not a very hard boundary, although as a student, I often perceived it that way. Because you're taught, okay, this is a very applied mathematics course, this is a very mathematical course. So I think that does not help the difference that people perceive between the two disciplines. And I don't know if that also resonates with other students, but I think that's my perspective on this. Yeah.
Thank you very much. I have one last thing also. I would start with you again, Marit. How would you answer to somebody that tells you, then why you do mathematics? Why should we pour money into mathematics if you're doing this abstract thing and we won't bring anything for the next 20, 30 years?
I think because science should not inherently be done to achieve an application. I think fundamental science is just what it is. Science we do because we want to know things. We want to learn more things. It's in our human nature. And I sometimes feel like there's a lot of emphasis on finding applications, being able to turn mathematics into a product. And I'm quite young and maybe a little bit naive, but from my philosophical point of view, I think that science as a whole, not just mathematics, should be done from the point of view of wanting to learn things, wanting to expand our knowledge, and not with the idea in mind of having a direct application. I think for applied mathematics also, they're not worried about the direct application all the time. They're just focused on the mathematics that they're doing. And that's also a big part that I like about science, that you're just trying to explore human knowledge. So I hope that answers your question a bit. And
absolutely. I love this answer.
I do sometimes feel that as a student, I don't have the full perspective of how a university works and how the world works, I think. But I sometimes feel like there's a lot of emphasis on getting results. And I understand why the system is built in that way, but I think it can also be in a way harmful to science itself. But I don't know the full picture, but that's just a feeling that I sometimes get. I don't know whether you have a more informed opinion on that.
There are some small areas in mathematics where it's hard to put the label applied or pure on it. And I'm particularly thinking of an area such as cryptography, security. Because obviously that is applied. Yeah, because it's important for society that when we try to have contact with our bank, and we all do that online, the bank doesn't even offer another possibility probably, then that must be secure. And then there also has to be research on things that do not exist, because who knows, at some point there might be a quantum computer and then all sorts of systems are all of a sudden broken. So we need to think about possibilities of building something that's post-quantum. And then building itself is often regarded as part of pure mathematics. But all the systems, does this actually fit on a smart card or on a mobile phone or on some other device, is an engineering aspect of it. I mean, we are willing to type in a 4-digit or maybe even 6-digit PIN code at the bank. If we would have to write a little program that lasts 15 minutes, then we would all go to a different bank. And so there is this practical thing that is important and that is really applied. It's where you have to talk to a computer scientist, to a physicist, and what fits on such a small little device and how is programming done efficiently enough. And okay, we have this numerical way of solving big matrix equations, but in this system it needs to be done with integers modulo 2 or something weird like that. Which of your systems still work in that context? And then we have the very pure mathematician who is taking all sorts of high-powered geometric methods for building such potential ways of encoding. So here, if you call it a difference, it completely disappears. Because you need a team with people with an interest in the various aspects, and you need to know what the other knows a little bit.
Yeah, sounds very interdisciplinary even.
I think it is.
Thank you, Jaap, for that very interesting answer. With this, we will end the podcast. We would like to thank both of you for putting in your time and being available for this recording. And we would also like to thank the FSC Radio Podcast for us being able to use their equipment. And also the listener for tuning in again. And we hope to see you next time.
Yes, thanks everybody. And at least for me, this was a very interesting discussion full of food for thoughts. In fact, there are a few things that I'm probably will ruminating over the next few days. But it was very nice. Thank you very much and very informative. If you like this episode, please consider sharing it with your friends and on your social media accounts.